my side project. I know everyone will agree, if you've been out of this building since the start of this conference, that air quality in Glasgow seems to be good, apart from the rain. But I mean, yes, that is true actually, and indeed, here is the prediction for today. So it actually turns out that you can, at the moment, check what the air quality is supposed to be or is most likely to be in Glasgow or anywhere in the UK, actually, at any point. And you can actually have data ahead a few days. Actually, the website, which is the DEFRA website, provides data for like 5 days, I think. So, yes, this is the prediction for today. And according to what is there, it says you should enjoy your usual outdoor activities. So probably you don't want to sit here. But yes, this is a very clean day. But unfortunately, it's not always the case. So there are days like this, and when it gets really bad, you can get some media coverage like this, which was published on a few days, I think, before February 27th, about how bad the air quality was going to be. And yes, the problem with this system, even though we already have it, is that the data. Okay, I think we'll do this before that. The problem with this system actually is that the data you get on this plot, which you can see here, is from in Glasgow 4 points. So if you think about it, you describe the whole of Glasgow with just 4-point measurements as regards NO2. So these are the points in Glasgow. People who live in Glasgow probably know this is better than me. Glasgow Curbside, and this the measurements you see on the top right from yesterday at 4 p.m. what the value is, and actually you will find that Glasgow is actually even better in terms of spatial resolution than a place like Cambridge, where we have come from. There are only 2 points that are used to describe the whole of Cambridge in terms of air quality data. The challenge with this is, first of all, the obvious one is that it's static. So, but research has shown that air quality varies a lot, both spatially and temporally. So this is static, and you cannot move it around, and you cannot see how it changes as you move around from place to place. The other thing is, if you wanted a pollution map, if you wanted to live here and go to an office in another side of the city, you don't know exactly what the air quality is going to be like in those places, because you only have data for 4 points. So something clearly needs to be done to make sensors smaller, cheaper, like we heard on Monday, and hopefully mobile, and also non-intrusive, so we can actually have pollution maps, like we know exactly what is going on. And here you will find what the regulations are, what are the numbers, what should they be, what do you expect. So you will find, if you compare these numbers with those there, that yes, it's actually quite low compared with the limits. So I think it's not too bad for today and yesterday, I think, so far. So then, what is the motivation actually for us to detect NO2? It is a very toxic gas, and it's 4 times more toxic than NO. So with NO, you can possibly say you want to, some of the limits are put at like 25 ppm, but with NO2, you begin to notice mucus irritation at as low as 10 ppm volume. So it is actually something that we need to monitor. If you consider the sources of NO2, outdoors is usually vehicular, yeah, and it is also worth mentioning that concentrations of NO2 inside vehicles can be 2 to 3 times higher than by the roadside. So that's obviously because you're probably, depending on the circulation in your vehicle, maybe you are taking in air from directly the exhaust of the car in front of you or something. So, and also in-house, it could vary a lot or could rise depending on whether you use some specific kinds of stove and stuff. So yeah, we need to actually detect NO2, monitor it. Also, because that helps us to be able to say for sure with certainty whatever results we get from health outcomes later on in life, to say for sure if it's anything to do with air pollution. Otherwise, at the moment, people just collect air pollution data and then collect hospital data and find a correlation. So we all know that graphene is an amazing material which senses everything, and that's a disadvantage. And this work, which Felice has also mentioned, also made my presentation a lot easier, was done essentially to produce single layer graphene at very high yield, produced essentially graphene. But one of the things that we discovered is that we can make these very selective to NO2 if only we used this well-known binder material called CMC. So CMC has been around for a long time, and actually, someone in 1942 already, Yackel, in 1942 already said that CMC can be oxidized in NO2. But that is something that people didn't really take note of, but we've used binders for different things, including in biomedical applications and stuff. So for this application, we basically use the same process as described earlier, and then we got the graphene ink at the end of that, and we could drop cast or print this. So we have some results. Just before then, I'll just mention that we characterized, so the results you will see are from this machine that we have used to characterize the system. So we have NO2 from 0 to 100 ppm, and ammonia the same, CO2 0 to 100%, and water as well. So what you will see here is gas sensing response to NO2 using just the drop cast material. And you can see that at 20 ppm, we get more than 10% response, and this rises as we go on. But we hit a problem just at 60 ppm because the material saturates, and then there is no response, even though you introduce higher concentration of NO2 into the system. But we verify the selectivity because the material essentially doesn't respond to CO2 and ammonia at all. So to be able to solve this problem, we decided to explore the aerogel route. So if I may just compare both of them, you see that the one on the left is the drop cast material. And what happens actually, why we see the saturation here, is because as the reaction takes place, the material is used up. So when the material is used up, you hit saturation and then you don't get any response again. But if you essentially go into the 3D layer, you can basically have higher sensitivity and a larger dynamic range. So we don't have this saturation anymore. And then we have responses in this form with a theoretical limit going to less than 100 ppb. And you can see also here the selectivity also verify that the material is just selective to NO2 as already predicted by Yackel in 1942. So the other thing we wanted to also measure was ammonia. This is important for applications such as breath testing. So it's been known and it's been found that actually ammonia in breath higher than 1 ppm could be indicative of renal failure. So if the normal passage of ammonia out through the body is through urine, and this is of course through filtration processes of the kidney. So if we begin to see ammonia in breath, then this is indicative of improper or failing filtration. So we basically used a zinc and polyaniline aniline composite, and then just drop casted as before as well. This actually is a work in progress, and we are still looking to improve the performance of this. The same system used to characterize as described earlier before, and then we tested the material as well and found that at 20 ppm we got a response to ammonia. We haven't tested this material for selectivity just yet. Uh, and then we essentially changed the concentration ratios of the two materials to get sensitivity to up to 5 ppm of ammonia, 10 ppm, 15 and 20 ppm were all tested for. Uh, just to wrap up, I would like to acknowledge these people, Dr. Stephen Hodge, who now works at Basarian. I'd like to acknowledge my sponsors. Thank you very much for listening.
What about the selectivity between NO2 and NH3 in your system?
You mean for the NO2 sensor?
Yeah.
We have already done that. You can ask. This was already done here and also here. We've tested and we found that just the level of response is just, I mean, is obvious to us that this is very selective to NO2 because this reaction actually is an oxidation of CMC. So basically, when you flow in NO2 into CMC, basically what it does is to attack the hydroxyl groups there, and yes, so what it does is to attack the hydroxyl groups, and you end up with these two mix, which basically tells you that the material is going to oxide. So there's the one on the left, which is the X ratio, then this is the original material, but the one on the right is the material now, the pattern has been oxidized. So you see the hydroxyl group replaced with the carbonyl group and carboxyl group. So this rolling acid, these are materials that have both carbonyl and carboxyl on the same carbon atom. So this is what happens, and this is why the material gets used up after some time. So this is actually a reaction that is specific to NO2. So it's not going to happen with NH3. And this is where the selectivity comes from.
But if you go back to the graph before, is it the saturation or?
This is just change in resistance compared with resistance presented in percentage.
Is it recoverable?
No, not in this form. I mean, the aerogel recovers, as you can see here, except for the drift, of course, which is kind of well known in gas sensing. But the aerogel recovers, but the the 2D form doesn't recover.
Thank you, Blue. Very nice presentation. I have just a question about CMC. Because, of course, CMC is highly soluble, relatively soluble in water. And, you showed two examples of, for example, air testing and also renal kind of testing. And these both have interaction with liquids and possibly water-based solution. So what's the stability of this sensor over time?
The breath testing, it did not have CMC in.
Okay, it's not CMC?
No, it's not both of them CMC. So the breath test uses zinc oxide and polyaniline. So it's only the NO2 sensor that has CMC in it.
And do you think this is going to be a problem with exposure to air?
So the results presented here were done in dry air, but also for the aerogel, this has been tested actually in humid environment, also in the same machine. You know this machine. In the same machine with water, different humidity percentage, and it's a white.
Aerogel or hydrogel?
Hydro.
Hydro.
Aerogel, sorry. So I think that's also why it covers.
I have a question. Who tested the temperature dependence and sensitivity of this response?
I don't have the graph, but for this one, we did another test at 100 degrees, and it did not improve the performance, unfortunately.
Because
CMC is not very stable at high temperature.
but is it sensitive because there's an oxidative process? Typically, it does have some temperature dependence.
I think the best way to have verified that will have been to do tests at relatively close temperatures, say incremental temperature levels, say room temperature and maybe 30 degrees and 35, 40, thereabout. But we haven't done that. We only did room temperature and 100 degrees, so like two different. So I do agree